This is FE Peer Review. The date is August the 20th, 2023. Sensible Lunacy, a debate about reality. Part 2 of question mark? Probably 3. A challenge to Lunacy Lander to do his own research. In this video, we are looking at a debate between Mr. Sensible and Lunacy Lander. And in this particular portion of the debate, I'm pointing out that Lunacy Lander made a number of unsupported assertions. My video purpose here is to challenge him to back up his assertions with evidence. In other words, to put a little bit of money where his mouth is. What are we going to cover today? We are going to cover, first, MAGE 2, lens distortion and how to correct it. There was a good discussion about that. And that led us to some misconceptions that I believe Lunacy Lander has about the human field of view and how we interact with our environment through our eyes, what that means, what we actually see when we look at the horizon, what we see when we look straight down. I've put together some little visualization tools in SketchUp here that we're going to use to hopefully clarify some of that. And then the next stop on our little tour is the Bolivian Salt Flats and Mount Tunupa as seen from the Salt Flats. Finally, we will pay a little visit to our friends at NASA, everybody's favorite governmental organization, to hear what they have to say about satellites. The conversation has to do with satellites and cell tower networks and how do our mobile phones use both. Last but not least, and related to that topic, we will visit Royal Caribbean Cruises FAQ page to find out more about how you can geolocate yourself in the middle of the ocean. So here we go. This is part 2 of the discussion between Mr. Sensible and Lunacy Lander. They started their discussion at this stage talking about the cameras on MAGE 2 and lens distortion and such things. And then Lunacy brought up the Bolivian Salt Flats, and that's what we're going to look at here. First the camera and then Bolivian Salt Flats. So we have, from my notes, Lunacy at 1:05. Lunacy gives us a discussion about camera distortion due both to the lens and to other factors. This is interesting, but the technical details aren't particularly important because fortunately it's very easy to identify distortion in the image by the simple expedient of keeping known straight objects in the frame. If they appear curved in the image, the distortion can be measured. This is precisely what Mr. Sensible did with MAGE 2 with the taut strings across the view area. So we can't discount the MAGE imagery by citing distortion. Any distortion that is in the image is known and can be corrected for. Mr. Sensible shows this at 1:14:30. He gives us an image showing the curve of the horizon with the strings, and the image has been post-processed to remove the curved strings so that the strings appear straight. And despite that correction, so that the known straight strings appear straight, the horizon is still curved. Walter Bislin also did a analysis, and Mr. Sensible mentioned that, and then it eventually did succeed in finding the link. I'm going to include the link to Walter Bislin's imagery in the description as well. At 1:10, Lunacy takes a screenshot from the MAGE image that has an arc that's been drawn over the horizon to show the horizon, and he overlays 8 of these to create a full circle. He's going down a confusing path here. It's going to be able to take a little bit of trick to sort this out. Lunacy has taken a screenshot from MAGE and shows that it takes 8 rotated images to create a full circle, when he says it should only take 4 if the camera field of view was a full 90 degrees. So I'm not sure why he thinks the camera field of view is 90 degrees. He gave some kind of reason that had to do with the particular camera and lens. whether it is or isn't 90 degrees is kind of irrelevant, but we're going to look at this point anyway. In the side chat, Dave McKeegan points out that the quote 90-degree field of view, typically it's describing the diagonal of the image, not the horizontal. Kind of like how they do with television screens, large screen TVs, the 48-inch screen is the actual diagonal measurement. That said, that 90-degree field of view does not mean that if you point your camera at the horizon and take a picture and then do that 4 times, you're going to get a full circle. I'll talk about that some more here. I'm going back to my notes. More importantly, this, Lunacy Lander's concept of what to do with the image here, represents a misunderstanding of perspective. The camera is pointed roughly level in the direction of the horizon. It is not pointed sharply downward. If it is pointed downward, it is only by a few degrees at most. If you have a field of view of 90 degrees on the horizontal plane, then rotate the camera 90 degrees, take a photo, rotate again, etc. 4 times, you will have a 360-degree panorama. You'll be back to where you started. But you will not have a circular image because you're not looking straight down. Take your 4 images and line them up in a row and you're going to see a nice panorama, but it does not create a circular image. It creates a pretty much straight image. So I'm going to back up. But you will not have a circular image because you're not looking straight down. You are looking at an angle. Looking at a circle edgewise and you see an ellipse, not a circle. We're looking at the 360-degree visible Earth view edgewise, with only a very slight downward angle. If you want to see the full circle, you need to be looking straight down with a very wide angle lens. How wide depends on your distance from the ground. Or you must be very far away, like a rocket near the moon. At 1:18:28, Lunacy says, like I said before, the 2 problems, I'm quoting here, like I said before, the 2 problems that we have is 1, we don't have a full 90-degree image from a 90-degree camera, or supposedly we have a 90-degree image from a 90-degree camera, but we don't have a 90-degree curve. So again, he's back to the 90 degrees, and why that is relevant to the curved horizon we see in MAGE image, he never explains. Why does it have to be a 90-degree camera? They're telling us it's a 90-degree camera. It's not a 90-degree camera. Why does that matter if we've shown already, as we did a moment ago, that the taut strings, which are known to be straight, and the image is distorted, so the strings appear curved, but when you take that image and straighten the strings out, the horizon remains curved. This is Walter Bislin's image that he also took from MAGE, and shows that when you adjust the image to straighten out the strings, the horizon remains curved. He took it from a different point in the video, so it appears a little different than the previous image. But it's the same exercise as we saw in the earlier image. We don't need to have a 90-degree field of view. We could have a 5-degree field of view, a 20-degree field of view, a 90-degree, a 120-degree. Wouldn't matter if we have straight reference lines in the image. We can correct the distortion. I'm going to take a look at a couple of other images. Earth from the ISS. Here in the upper right, we see an image taken from the ISS, and we see elements of the ISS, like the solar panels in the top right corner, which we know to be straight. We know those solar panels are not curved, and yet they appear curved in the photo. So we have a good reference for the distortion in this particular photo by virtue of having those straight lines of the solar panels showing up as curved. We could look at a different image. It's taken with a different kind of camera and lens and have straight lines. I'm not sure that's actually a photo or a graphic. Let me find one that I'm more confident is a photo. Well, it doesn't really matter. I think I've made my point. When you've got known straight lines in your photo and they appear curved, you have the means at that point to correct for distortion. Okay, so back to what we were talking about. So I'm gonna show you this little model here. This is a sphere. Call it the Earth if you want. Call it a basketball. It's all the same to me. It's a sphere. And I've created something I refer to as a station point. I put it on the top of our sphere here. That little structure there represents an observer at the point of that little pyramid-like structure. The observer's eye level is up there. And the observer is looking off in this direction, perpendicular to the observer's position. So that dashed line is perpendicular to the observer's position. And off over here somewhere I've put another station point just to match the first one. Now we're going to have the observer looking off. Now we're going to have the observer looking off towards that second station point. Get this lined up where I want it, approximately in the middle of the screen. Makes it easiest to see. So this here is a circle around the observer. It's roughly tangent, it's not quite, but it's nearly tangent to the observer's view line against that sphere. The observer is looking straight ahead. Right there. That's the line. This is the actual horizon on this sphere here. And that's the line I drew, which wasn't quite in the right place, but it doesn't matter. My point is that the observer is looking straight ahead, and this line going across the middle here, which appears very slightly curved, is not a circle. I should say it actually is a circle, but it does not appear to be a circle to the observer. I'm going to zoom back out. To the observer, it appears to be an ellipse. There's our ellipse. Now, in reality, it is a circle. It's a circle, all right. But when you're looking at it from a low vantage point, it looks like an ellipse. So these are things that have to do with what we see around us when we look at the horizon. Imagine you're on a boat out in the middle of the ocean, with no land in sight, and you're standing on the deck of that boat and you're looking off here in this direction, and then you gradually turn and look all the way around, full 360 degrees. You understand that you're seeing a circle, and if you were looking straight, if somebody else was looking straight down on top, looking straight down at you, that point on the water that you're actually looking at on the horizon would appear to that other observer to be a circle. But you, when you're standing on the ground there or on the deck of the boat, you don't see it as a circle. You see it as an ellipse. So that's something that Lunacy Lander needs to think about and sort out in his mind. What are you actually seeing when you look out towards the horizon? I'm going to say this was all based on a globe here. He should do the same exercise without presuming a globe, but rather presuming a plane, a flat plane. So the question becomes then, is this an infinite plane, or is it a finite plane with an edge? And if we're looking at the sort of traditional flat Earth concept of a sort of a flat circle, a disk, um, what are you seeing when you look out at the horizon? Are you seeing all the way to the edge of the disk? Are you seeing simply to whatever is in the way? No, whatever obstruction there is. So if you're out in the middle of the ocean, on a deck on a boat, nice and high up above the water, so you're well above the waves. What's your model? How are you figuring out what you're seeing when you look at the horizon on a flat plane, whether it be an infinite plane or a disk? So I invite Lunacy to work on that and come back with some more concrete ideas about what's being seen there, because we have these concrete ideas with regard to a globe. It's basically pretty simple geometry. There's some complications that have to do with atmospheric refraction, the fact that we're not looking through a vacuum, but that there's gases in the air that affect what we see. But those are pretty minor. The impact of those is measurable, but is minor. Doesn't matter. It's not important. I'm going to show you one other diagram here. We're looking at a circle, and we've got an observer. Now we're looking at this from a kind of side view from that sphere. I've just flattened it out to a circle. And we've got an observer standing here, and that's the observer's eye level. The observer is looking out to a point that's tangent on this sphere, on this circle here. So anything over here, beyond this line, anything over here, can't be seen by this person because the view is blocked by the surface in between. So they can see as far as there, but they can't see the ground surface over here. Now, if there was a mountain over here, they could see the top of the mountain, but they wouldn't be able to see the bottom of a mountain. Not if they're standing on a curved surface. So now we're going to move on to the next thing. Lunacy says the flat earth is not a big focus of his, just something he follows. He then mentions the Bolivian Salt Flats. I'll add here that they cover 10,000 square kilometers, and as described in Wikipedia, have a variation in surface elevation of, quote, less than 1 meter normal to the Earth's circumference. So that's how it's described in Wikipedia. Less than 1 meter normal to the Earth's circumference. Lunacy says, there's no curve there. That's a quote. There's no curve there. He's referring to the Bolivian Salt Flats. I will point out that this is an unsupported assertion and a particularly interesting one because it opens up yet another opportunity for Lunacy to do some of his own research. You see, he's given me an unsupported assertion. My answer to that is, why should I believe you? Give me evidence. So here's an opportunity for Lunacy to gather some evidence to support his assertion. Bolivia is a bit far from the USA, but well within normal international travel. He could actually go there himself and check for curve if he wished. He would need to determine an appropriate way to test for flatness and curvature. But that's, details. Figure out how you want to do your test and then go there and do the test. Here is the Bolivian Salt Flats as seen in Google Earth. Let's take a look here. Some interesting things to see. So 10,000 square kilometers, 10,500 and some square kilometers. The north end of the Salt Flats, there's a volcano called Tunupa, right where I'm circling the mouse. You could get about 100 kilometers away by going all the way across to the southern part of the flats, 100 kilometers away. If you were standing at the bottom here, you'd be 100 kilometers away from Tunupa. So, my suggestion, Lunacy wants us to believe that the salt flats are actually flat as opposed to level. Level, let's say, if he wants to say that the salt flats are actually flat versus the salt flats are level as globies describe level, he can tell us, he can show us by going there and doing this observation. He can stand 100 kilometers away, look to the northwest, and see the peak of Mount Tunapa. I can only think of 3 things he might see if he actually were to do this experiment. He might stand down at the south end and look across and see all of Mount Tunapa. I mean, he's using a good telescope or something, we're assuming. He might be able to see the entire mountain all the way down to the base where it meets the ground. There's a road down here, a little village. Could be able to see all the way down to the point where it meets the salt flats. That would be something like this. Let's see. Now he's standing over here on the left, looking off to the right, and there's the mountain, and he can see from the top of it to the bottom of it. So that would be one possibility. He might see all of it. Another possibility is like what we looked at before. He might be standing here looking off to the mountain and be able to see the top of the mountain, but his view of the bottom would be blocked by this ground here. And I'm going to mention that the mountain actually has quite a wide base, so he might be standing over here and be able to see the top of the mountain but not see its base. If you go to Google Earth and look at the terrain, get this out of the way. The mountain peak is 1,648 meters above the salt plains, by the way. And if you look at how the elevation changes, this over here, it's rather steep all along from the top coming down, and then from here it's much less steep, kind of gradually tapers down to the ground. So there's something Lunacy Lander can do if he wants to do a bit of his own research and provide some support for his currently unsupported assertions. Go back to my notes here. So what might he see? He might see the entire mountain all the way down to the ground. He might see only the top part of the mountain, and then of course there's the third possibility, which is he might not see the mountain at all. I'd be thrilled if he would go down there and do that and record what he sees. Got to have decent viewing conditions, weather matters. That can be dealt with. So Walter Bislin has on his Advanced Earth Curve Calculator a nice little feature here. I put in the height of Mount Tunapa above the plane of the salt flats. And then I put on the left the flat Earth visualization from 100 kilometers away, and on the right a globe visualization with no refraction. I think I've got refraction set to 0 here. Anyhow, so I put an observer height of 1.5 meters. You can change that to 2, you can change that to 1. You'll see that it doesn't have much of an effect on the results. I've got a target distance of 100 kilometers. I've got a target size 1,648 meters. That's the top of the mountain to the surface of the salt flats. And what we see from the curve calculator, according to these two models, we've got a slight drop to the horizon for the globe model, whereas the horizon is at eye level. For the flat Earth model, that would imply an infinite plane. And then if the flat Earth is not an infinite plane, and you're seeing all the way out to the edge of the ice wall or whatever is out there, there would still be a little bit of drop. We can get into the geometry of that if necessary, but I think it's more important to do the observations. So on the left we have the mountain, and on the right we have the mountain, but we are not seeing the entire mountain. We have 590 meters hidden. 590 meters of the mountain is hidden. So according to the globe model. So if, Lunacy, you go out there and you take a look at Mount Tunapa and you can't see any of this stuff down here, I'd love to hear your explanation. Why you can't see it? Because on a globe Earth, you shouldn't be able to see it. All right, I've decided I'm going to slip one more little visualization in here before we move on. This might be useful to Lunacy Lander and others watching this video. And this has to do with the normal human field of view. So we're not talking about cameras and stuff like that. We're talking about our eyes. On this image here, we've got a top-down view. We're looking down at this guy's head here, and he's looking straight ahead. And there's a central part here that occupies about 60 degrees of his field of view. And then there's a peripheral, that extends out to about 120 degrees. And this is a top-down view, and here's a side view. Same thing. Our eyes tend to favor down rather than up, but it still adds up to about 120 degrees. And of course, this is just a sort of typical, every person's a little bit different, but that's the normal range. So if you were to stand and look at the horizon, stand on the beach, look at the horizon straight ahead, you would not be able to see your toes. But if there was some object down there that was moving, as it moved forward, at a certain point you'd see it at the edge of your peripheral vision. We tend to see moving objects at our peripheral vision rather than still objects. So if there was a rock down there, you probably wouldn't see it if you're looking straight ahead. But if it was a crab walking across the sand, the movement would catch your eye, and then you would instinctively look down and see it with your central vision. So that's something to keep in mind when we're talking about what we see. We go and stand on a mountain and look out at the horizon, or go and stand on the beach and look out at a horizon, and we can talk about what we see, but as soon as we want to show what we see to other people, we have to resort to cameras. And that, of course, immediately introduces distortion related to the camera. So what I'm looking at here, what I'm suggesting here for Lunacy Lander is forget the whole camera talk for the moment and just think about these images I'm presenting. The next time you're out and about in the world, think about how you're seeing things this way. So I've made a little model here, and what I've got here is, here's a top-down view. Just like that guy that was looking straight ahead and we saw a top-down view. This is a 60-degree triangle. That angle there is 60 degrees. So and he would be able to see 60 degrees the other way as well. So what I'm going to do is I'm going to create a cone which represents a person's field of view. So this is a field of view of a person looking straight ahead. Their eyes are right here and they're looking off this direction. And this is them looking up and down and side to side. This is all approximate. It's just in order to convey a concept. So we don't need to worry too much about, like I mentioned, that we tend to favor down a little more than up. Not important for our purposes at the moment. I'm going to make that surface there transparent so that we can see what's going on here a little bit better. And I'm going to get rid of this and that. Okay, so we have a cone that represents the field of view, and that cone is oriented so that it's looking straight off in the direction of the upper right. I'm going to make a copy of that. And I'm going to rotate it so that it is looking straight down at the ground, as if you were looking down at the ground. So imagine you're standing in the center of this here, and these are your eyes are right here, and you're looking straight down at your feet, and this is what you're seeing around you, around your feet. And here, this one, you're looking off to the right, and you can see up and down and to either side. Okay, I'm going to take this cone of vision now, this field of view, grab it by the point there, that's the eyes, and bring them over here. So the person standing right here and looking off to that little station point out there, he can see off to his left, he can see off to his right, the station point straight ahead. and he can see down. Now I've put his eyeballs right on the ground. I should really lift him up a little bit off the ground. Let's do that. Let's move him up a little bit because he's not lying on his stomach. So you see he can't quite see his feet here, but he can look out a little bit and see down to the ground. But at a certain point, if he's standing on a curved surface, he's not going to be able to see things that are blocked by the curve. It's just like we saw before. I don't need to repeat that. Okay, so that's him looking straight forward. And he's looking out at that station point, and what he's seeing as far as a horizon is something out there on the edge of the circle, on the edge of the sphere out here. That's what he's seeing as a horizon. Come in here a little bit closer. Okay, now as you can see, we weren't seeing a circle, we were seeing a line that's just a very small fraction of a circle. Now we're going to see what happens when he looks straight down. So let me get rid of this one and bring this one over. So here he is. After a hard night out, Saturday night, he wakes up in the morning with his face in the gutter. Can't see a thing. He's looking straight down at the ground. Doesn't see a single darn thing. But as he comes to and he starts to come back to his senses, he gets up and stands up. And there he is. He's standing up now. And he's looking down at his feet. And he can see a little circle of land around him. He's not turning his head, he's not moving his eyes, he's just looking straight down at his feet, but he can see a little bit else of what's around, you know. If some bug goes walking past, he'll see the bug. If it's in his peripheral vision, he'll see the bug. If it's something that's in the central vision, he'll see that quite clearly. But one thing he's not seeing is a horizon of any kind. He's just seeing a patch of ground. But now let's suppose he starts going up. Now he's standing up on top of a very tall ladder, and you can see quite a bit more of the surface below him. Nonetheless, even though he can see a great deal more of the surface below him, he still cannot see most of the sphere that he's standing on. So let's keep moving him up. A little less than that. That's good. So I'm going to ask you to ignore the stuff out here. He is seeing this inner circle here. And then the white part is blocking his view of all the stuff down here. You see, he's standing up here looking straight down. Now, he's not seeing half the Earth. He's only seeing a very small part of the Earth. And now he's going to go up a little higher. So now he's gone up higher, and the entire sphere is fitting inside his field of view, but he still can't see the stuff over here because the sphere itself is blocking it. If he keeps moving away, now it fits easily inside of even his central vision. Remember, his central vision was only a third of the total. A half of the total, 60 degrees. This is 120. So it was a half of the total, the central vision. And this sphere is fitting nicely within the central vision. But is he still seeing, but is he actually seeing half of the sphere? He's not actually, because here's the, if that's the North Pole, here's a point on the equator. Let's draw a line from this point on the equator. So there's a line that connects his eyes, straight line, to a point on the equator. And as you can see right here, where I'm circling the mouse, he has to be looking through the Earth to see the equator. In other words, his view is being blocked by the curve of the Earth, and he can't see the entire an entire half of the Earth. He can only see this part right here. Now, if you figure he just gets farther and farther away, well, then all that's going to happen is he'll see more and more. But if you do the math, you have to be infinitely far away to see half the sphere. And that's why when you look at the famous 1970, was it 1972 blue marble? Yeah, 1972 blue marble photo. You're not seeing half the Earth. You're seeing less than half the Earth, because even when they were as far away as the moon, it wasn't far enough to see an entire hemisphere. So that's what it means to see the curved horizon. You have to be looking straight down, and you have to get higher and higher until the Earth fits in your central vision. At that point, you can say that you've seen the curved horizon. That's how I like to visualize it. Think about that when you're out looking around the world. And maybe you'll start to see things a little differently. Okay, last part of this little video, we're going to be talking about cell phones, satellites, and cell towers. There's a brief conversation on that subject in this discussion between Mr. Sensible and Lunacy Lander, in which Lunacy says a few things, and I'm going to repeat them here now, and then I'm going to play the little bit of video. He says, even your phone doesn't connect to a satellite. I'm going to point out that there's a little bit of, in my mind, a little bit confusion. They're not really entirely clear, either of them, what they mean by connect. It could be used two different ways, and it's not explicitly clear which ways they intend. So you could be talking about the actual conversation you're having with another person on your phone. There's a signal being relayed back and forth between your phones that allows you to hear the other person. That's one kind of connection on your phone. But the other connection is simply a signal that identifies the location of your phone. Your phone is receiving location information. So that's a different kind of connect. And it's not entirely clear which one they mean, but I just wanted to mention that. Another thing that Lunacy says, your GPS is all tower-based. Anything in your phone is tower-based. And then he also says your phone will never connect to a satellite ever. So let's hear it directly from our gentleman here.
Right, but even your phone doesn't connect to a satellite.
No, my phone...
And even the AirTags only connect to other Apple phones.
Yes, they're receiving signals from satellites with regard to GPS. That's how GPS works. Each GPS satellite basically says, this is the exact time and this is where I am. That's it.
But your GPS is all tower-based. Anything in your phone is tower-based.
No, a GPS...
Absolutely. It does not connect to a satellite. Your phone will never connect to a satellite, ever.
But then, okay, what about...
All right, that's enough on that. Okay, I'm going to say a little thing about my phone. I do indeed need to be connected to the cell tower network if I want to look around on the internet. And so, for example, if I'm going to go on a trip, which I'll be doing next week, I may find myself wandering around in a place where I'm concerned I might not have a signal. I would like to be able to use my Google map on my phone. So what am I going to do? Where I have a signal, like today, this evening I'll be doing that, I am going to download some maps onto my phone. So all that map data is nicely stored on my phone. And then if I should be wandering through the countryside in that location and I don't have a cell phone connection, I can still pull up my map because it's now loaded onto my phone. And this is the important part, there's going to be a little green dot on that map that shows me where I am on that map, even though I don't have a cell phone connection. I won't be able to make a call, but that little green dot will be there and it'll move as I move. And that's because that little dot isn't relying on the cell phone network, it's relying on satellite data. Now that's standard in everybody's phone these days. So we're going to look at why that works. And I have a question for Mr. Lunacy he can think about. Why is it that you can use a device like a phone if the map has been downloaded, or a custom or a specific device made for the purpose, which we'll look at in a moment, on a boat in the middle of the ocean. You can be out there in the middle of the Atlantic Ocean, and there won't be a cell phone tower within hundreds, maybe even thousands of miles of your location, and yet you can track your movement across the ocean on your little handheld device. How can it do that using a cell tower network when there are no cell towers within hundreds or even thousands of miles? You need to explain how these cell towers can actually accomplish that, because that's what you just claimed. So you need to be able to show how that works in the middle of the open ocean. Now, there's another claim that we can make, and that's that it doesn't use cell towers. It uses a satellite network. And your device is communicating with the satellite network. It's receiving a signal from satellites. That's the other claim. And now we're going to take a look at some information in support of that claim. Here's a company called West Marine. There's lots of companies just like this, and they're selling Garmin devices, like those little things people have in their cars. This is a little handheld Garmin device, $350. You can buy this thing yourself for $350. And it's intended for navigation on ships. Here's the GPS Map 79 SC handheld, $350. It's amazing how cheap this stuff is. How does it work? Well, come down here. Features. Supports multiple satellite, here it is, supports multiple satellite constellations. GPS, that's the US-based satellite navigation system. GLONASS, that's the Russian system. Beidou is the Chinese system. Galileo is the European Union, and I'm not sure what these other two are. I didn't bother to look them up. So it's this device here works with all of those satellite systems. That's what it claims to do anyway. Here's gps.gov. This is the website operated by the US government, who we know is the bad guy and can never be trusted. And it's got lots of good information on the GPS network. I'll have a link to that in the description. Here's the poster that's referenced right here. I've got it enlarged here so we can see it better. It describes the basics here. GPS is a constellation of 24 or more satellites flying 20,350 kilometers above the surface of the Earth. Each one circles the planet twice a day in one of 6 orbits to provide continuous worldwide coverage. And then it describes in a little 4-step explanation here how a GPS device on your vehicle locates where you are. All very nice. But of course, why on earth should we believe that? It comes from the US government and we know they're full of lies. Well, here's something to think about. This is the NASA website for the ISS. Link in the description. If you want to doubt that those satellites are up there, you can see them yourself. With your own eyes, you can see them. You don't have to trust NASA. You don't have to trust the US government. Here's the NASA website that tracks the ISS, and it's got this nice little map here with a line that's showing you the path of the ISS. If you follow this for a while, you'll find a time when it happens to be passing over your location at night. I've had 2 occasions to see it myself at night, and it went through the sky just on schedule, just as it said it would on the website. I looked up in the sky at the time that it was supposed to arrive, and there it was, and it made its way across the sky on its way to wherever it was going next. So yeah, you can see this thing yourself, and you can connect up with your network of flat earth interested colleagues around the world and find somebody who happens to also be in its path that same night. So maybe you know somebody in Australia, or maybe it's going to be passing over Europe. You can find someone who's also going to see it, and you can communicate with them. And so you record when it passed over you, and then they record when it passed over them. You get the time. You can figure out how long it took to go from over you to over their location, and how much time went by, and you're going to find that it was incredibly fast based on the distance. You can probably pretty well calculate the speed. You can estimate the speed based on the path according to this, and what you're going to find is that it matches what's on the website here. So you're going to have to explain, if all of this stuff about satellites and space isn't real, going to have to explain how this object that you saw on schedule as predicted, and which your colleagues saw on schedule as predicted thousands of miles away, managed to get from one location to the other, you're going to need an explanation and evidence. So now if you have a problem with satellites, I encourage you to give that some thought. It's a little experiment you can do yourself. It's a bit of research you can do for yourself. You don't have to trust anybody. Last thing we're going to look at here is, as promised in the previous video, the Royal Caribbean Cruise website. On their frequently asked questions page, will my phone work on board a Royal Caribbean ship? Yes, the Royal Caribbean works with cellular networks to provide the ability to connect your device through cellular at sea. Rates depend on your provider. Additionally, another option for staying connected without using your cellular data is connecting to VOOM, the fastest internet at sea. VOOM allows guests to stay connected via Wi-Fi with a variety of packages to choose from. So, what is VOOM and how does it work? Well, here's the answer. Royal Caribbean is the only cruise line with high-speed internet at sea. Whether you have your phone, tablet, or laptop, VOOM allows guests to stay connected. VOOM is available on board all ships fleet-wide. Each one of our VOOM ships gets its signal directly from a satellite beam dedicated to our ships that orbits closest to Earth, allowing us to offer fast and reliable service. So it's an satellite-based internet service that works when you're on one of their ships out in the middle of the ocean, thousands of miles from land. Once again, no cell tower network to tap into. So, my friend, Mr. Lunacy, there are some things to think about. You might want to do some research into these and learn more how they work. I think this video is long enough. We've got one last subject we're going to cover in the third video, which is a subject to my heart. It's the bridge and how it's changing shape due to temperature changes. That'll be a lot of fun. The towers that are not parallel to each other because they're so far apart and so tall that they account for the curvature of the Earth and all of that. We'll have pretty pictures to look at, some diagrams. That's all in the next video, but it's going to be probably 2 weeks before I can put another video out. I'm going to be traveling, so I will not be around much. Anyhow, hope you all enjoyed this. Have a great day. Bye-bye.